Hello and welcome to my series Learn Radiology with Dr. Anil Joshi. Today's topic is about MRI physics and that also 3D image acquisition. Now how a 2D image is acquired, how a 3D image is created, how a volume is created, that all we are going to see in this lecture but in a simplified form. So today's topic 3D imaging acquisition on MRI physics. Let's going, but not before we disclose, acknowledge and disclaim. Most of the material in this lecture is we have used from the departmental day-to-day lectures which are going on from many years. However, some of it is borrowed from the net, which we have confirmed that is a royalty free. However, still we acknowledge with thanks from those from whom we have got this. With this brief, let's get going to the today's topic, imaging acquisition. It is very important if we are going to see how a 3D image is considered, right from how the image is acquired, how the data is analyzed and how it is sliced, that all we are going to see in this lecture. Now following are 4 steps in image acquisition. First is preparation, excitation, spatial encoding and signal acquisition. After that only we can go to 3D image acquisition. Now all these 3 things we'll see in this lecture today. Let's come to the first topic, that is the preparation. The preparation of patient is done in following way. The patient is placed in a static magnetic field produced by a magnet of MRI scanner. In living tissues, there are lot of hydrogen atoms included in a water molecule, and water is abundant in body. Human body has got more than 75% water. So these molecules are abundant. However, they are not only as a free water but they are also in the fluid, and different tissues has got different concentration of hydrogen in them. The protons, the nucleus of the hydrogen, possesses an intrinsic magnetization called a spin. This is the intrinsic activities going on within. The spin magnetization vector processes or rotates around a magnetic field at a frequency called as Larmor's frequency. There is a separate lecture covering what is Larmor's frequency. Now this Larmor frequency is proportional to the magnetic field intensity. The resulting magnetization of all protons inside the tissues align parallel to the magnetic field. The parallel magnetization scale with the magnetic field intensity. Therefore, basically a 3D scanner will have twice the values obtained from 1.5 T. Additional sequences can also be performed to manipulate the magnetization to produce the image contrast. For example, inversion preparation. There are a lot of different sequences. Here we are going to see few of them, but most of them are covered separately in different lecture. During the image acquisition process, a radio frequency pulse is emitted from the scanner. When tuned to the Larmor frequency, the RF pulse creates a phase coherence in the precession of the proton spin. The duration of RF pulse is chosen such that it tilts the magnetic spin, that is the spin magnetization, perpendicular to the magnetic field. When receiving coil, that is an electric conductor, is put in the vicinity of the tissues, the transverse magnetization that still rotates as Larmor's precision will generate an electrical current in the coil by Faraday's law. You are also aware of it, how it is that magnetic field, how it can get converted into electric current. This is called, or this is the principle of nuclear magnetic resonance, that is NMR or MRI. The NMR signal is attenuated due to the simultaneous relaxation process. The loss of coherence of the spin system attenuates the NMR signals with a time constant, and this is called as transverse relaxation time or T2. Concurrently, the magnetization vector slowly relaxes towards its equilibrium orientation that is parallel to the magnetic field. This occurs with a time constant called as spin lattice relaxation time or T1. The contrast in MRI images originates from the fact that different tissues have, in general, different T1 and T2 relaxation times. As this is especially true for soft tissues, it explains the extent of the soft tissue contrast in MRI. Now, what is the spatial encoding? Spatial encoding of the MRI signal is accomplished through the use of magnetic field gradients similar, that is, the smaller additional magnetic field with an intensity that linearly depends on the spatial location. Spin from proton of the different locations will precess at slightly different rates. So, different location, different tissues will have different precision. The portion of the gradient coils and associated current that is perpendicular to the main magnetic field causes a force, that is Lorentz force, on the coil. The gradients are turned on and off very quickly in this process, causing them to vibrate. Now, what this vibration causes? The vibration will produce most of the acoustic noise during the MR image acquisition. Now, you know importance of the reduction of noise and increase of the signal, that is improvement in SNR is very important as far as image resolution is concerned. Now, signal acquisition. When using a magnetic field gradients, the obtained NMR signal contain different frequencies corresponding to the different tissue spin positions, and that is called MRI signal that we have seen. So, it will be different tissues will have different signal. After sampling the analog MRI signal, is digitalized and stored for processing, which consists of a separation of the signal contribution from the different spatial locations presented by a pixel in the final image. So, that's how a pixel of particular tissue in spinal image will be different, and because of that difference we'll get different tissues identification on the image, otherwise everything will look same. So, for this there has to be different signal, different tissues has to give different signal, it has to give different pixel brightness, that will give a better image. This is achieved by mathematical operation called as Fourier transformation. An extensive lecture is covered about the Fourier transformation. Please visit our website and our YouTube channel for that. Now, what is 3D scanning? In MRI, there is lack of radiation exposure and it has rich soft tissue contrast. MRI has inherent 3D imaging capabilities and hence it provides images in all three orthogonal planes, that is identifiable existence of three-dimensional images on the monitor, as well as oblique or even double oblique orientation is possible because of this characteristic. Now, let us know how it is made possible. Usually, the images are two-dimensional, where the MRI images are usually presented in a slice from top to bottom. However, using sophisticated computer calculation, these 2D dimensional slices can be joined together to produce a three-dimensional model or the area of interest being scanned. This is called a 3D MRI. Now, how the slices are achieved? Okay, you have got a volume data. Volume data can be by two methods, we will see it subsequently. But you have to obtain the volume also and you have to retrieve also. Let us see how it is done. MRI signal consisting of protons in a thin slice, that is 2D, and apply magnetic gradients in two directions parallel to the plane will produce two-dimensional picture. This will create an image of a single slice, that is two-dimensional image. If it is repeated many times, a stack of slices will be created that together will build a 3D volume, and that will be called as multiple 2D or in short form M2D. Alternately, signals can be obtained from protons in a 3D volume directly and use the 3 magnetic field gradients to figure out from where these frequencies are coming. So as simple, there will be a creation of 3D image directly by 3 magnetic field gradients. So we have got choices now. We can have 2D also as well as 3D also. Now this is where 3D volume data is created in the form of a 3D data sheet. Such images are processed to create a slice to a 3D volume as if scanned only once. So big volume, if it cannot be separated, will look like a same. So as though it looks like it is obtained at the same time. This is called as 3D scanning. Even today, 2D scanning is preferred for some specific reasons. It's a different topic, will be covered in different lectures. Even though 3D has many additional benefits, or best ways to have both. However, in future, more and more 3D will be preferred. So even though today certain machines go from 2D by stacking the slices to 3D, a direct 3D volume acquisition will be possible in the future. Technically, most of the MRI images are 3D and most of the scans encode their space in 3 dimensions. Taking multiple slices of 2D windows, some diagnostic scans are even interpreted in a 3D format. We have seen how they are stacked and this is made better. This is a better visualization of anatomical features and details. So everything has got its own advantages and some benefits and versus some losses or some deficiencies. Now 3D is a viewing technological module and not a limitation. So for MRI, when high definition 3D images are available in volumetric form, any preferred valuable slice can be available. So you got a 3D data volume. You want to extract axial, you want to extract coronal, or you want to make 2 oblique sections at same time. Everything will be possible since you got a volume data. Now with that, we are coming to end of lecture. I thank you for giving me your valuable time. There are a lot of lectures on our YouTube channels in different lectures, different topics are covered. There are different ways in which they are produced. Do visit our website as well as our YouTube channel. Thank you, goodbye and take care. See you in next lecture.